thank you very much, everybody, and thank you for the organizers. I mean, this is looking like a great conference. I think this is bringing a lot of value to everybody. So I think we really need to thank the organizers. I'm going to talk a bit about Scikit-Learn. This is going to be a big picture talk. I won't go too much into details. And you can see it as an intro to a tutorial that Andy Miller is going to be giving tomorrow. So once again, this is a big picture talk about things like the vision and how we run the project and why we structured the project as it is. It's a bit of a way of telling you why Scikit-Learn is built the way it is, at least the way I see it. So let me start with the vision. And we think of Scikit-Learn, at least I think of Scikit-Learn as an enabler. That's one reason that got me motivated with it. We think that it's important that machine learning should be accessible for everybody and for everything, every application. And we like to say that Scikit-Learn is about machine learning without learning the machinery. That is our goal. So just to give a bit of an intro, I don't know what your background is, so let me talk for a few minutes about what machine learning is, because I don't know how familiar you are with it. And my definition of machine learning is that it's about predicting from data. It's about learning predictions. And if we want to look at it in a historical perspective, in the 80s, people were building artificial intelligence models by building things that looked like decision rules. So you'd build a set of rules, a set of nested rules that would allow you to make decisions. Now, this was extremely time intensive. So as time went by, people started learning these rules from observations. So basically, you want to learn how to differentiate cars from oranges. Well, if you present enough cars and oranges to a system, then it will learn it. And then as the theory went on and as the problem became clearer, people started having a statistical standpoint on this more and more. So if you look at the literature, more and more the machine learning is seen as a statistical learning problem. Basically, the idea is that you're going to model variation between your observations as basically random distributions. Noise, if you want to put it this way. And these days, well, everybody's talking about big data. And my vision on big data is that it enables us to have a huge amount of observations and then to combine many, many simple rules. And there's this quote that I like from Steve Jurvetson, who is one of the trendy VC in the Silicon Valley, so somebody who makes a lot of money. And he says that big data isn't actually interesting without machine learning. So I find that at least a few years ago, people would talk a lot about big data. People would be, basically picturing themselves as sitting on top of a pile of data. But if you have this pile of data and you have nothing to look at it in a clever way, well, it's not useful, right? So that's why machine learning is useful. So to give you an example, say I'm coming back from my vacations and I've taken pictures of my friends who were on vacation with me. So I've got Andrew, Bill, Charles, and Dave. And the machine learning problem is to be able to tag these pictures with the names. So Facebook is doing this for you. So I'm going to start with a database of images that I have already labeled. And then comes a new image, and I'm going to try to put a label to it, right? And these images are not perfect. The training images, so these ones, are not perfect, and the test image, the one that I want to label, is not perfect either. They have noise. So one very simple method to do this would be to store all the images that I already have in the database with the labels that go with them, so the names. And now if I have a new image from one of my buddies with whom I was on vacation, I'm just going to find the one that is most similar to it for a certain similarity in my database. So the one that looks closest, and then I'm going to say, well, if the closest image is an image of Dave, then my new image is probably Dave too. Okay? That's a very simple method, but it's an existing one in machine learning, and it's known as the nearest neighbor method. So just to check you're not sleeping, how many errors am I going to get on the database if I show it images that are already in the database? No errors. I've kind of screwed up the slide because I should have hidden this, right? So why am I getting no errors, right? So I have a bunch of images that are already labeled. I come up with an image that's in this database. I show it to the algorithm. Which one is going to be the nearest? The same image in the database. So I'm making no error. Do you think that's any useful judge of the kind of errors you'll be doing in real life? No, it's not, right? If I come up with a new image, it's going to be harder. There's this quote from Niels Bohr who says that prediction is difficult, especially when it's about the future, okay? So the important message here is that your test data, the data that you haven't seen on which you're going to try to do the prediction, is not the same thing as the trained data, and that is the core problem of machine learning. Okay, let's take a very simple example. So in French, we have a saying that is that we worry about predicting the age of the captain. So one thing I could do is that I could worry about predicting the age of the captain using the size of the ship. Hopefully bigger ship means older captain. Okay? And I'm going to try a very simple model. I'm just going to say, that a linear version. The bigger the ship is, if I have a ship that's twice as big, then maybe the captain is twice as old. Okay? So that is the linear regression problem, right? It's no different from what we know in statistics, in basic statistics, linear regressions, right? Okay, but I can do something more complex like this. So which one of the two models do you prefer? Do you think is better? So the line, the straight line, or the wiggly line? The straight line. Well, you're telling me the straight line, but the wiggly line actually fits the data much better, right? The error is much smaller. Right, so we're capturing noise. That's exactly the problem. We believe, we have an intuition that this set of points actually has noise, and that with this wiggly line, we're just capturing noise. So this is known as the problem of overfitting. And it's back to the idea that minimizing error on the trained data does not control the error on the test data. So if you minimize this error too much, you're going to be also capturing noise. So that is a critical concept in machine learning. So what we're going to do is that we're going to prefer simpler model for a certain definition of simple. So here we've introduced some form of regularity in our model, and we have a family of different models that are more regular, simpler. This idea is the idea of regularization in machine learning. Regularization in general is the idea that you're going to push your solution towards simpler solutions. And the intuition, if you're a statistician, is that we're going to be balancing the number of parameters to learn with the amount of information that our data is giving us. So less data or more noise mean that we're going to have to prefer simpler models. And finding this trade-off is a difficult problem, but Andy will tell you how to do this tomorrow. So if you're a statistician, this is a typical bias-variance trade-off. Suppose you're throwing arrows at a target, and if you throw them high, it's harder. So if it might be interesting to throw them to aim right below the target because you are doing systematical bias. The average of your points is not exactly on the target, but if you look at the average error, it's actually smaller, right? So quite often I see people who are not experts in statistics telling me that bias is a very bad thing. It may not be if it reduces the variance. So we have a bias-variance trade-off. Another challenge we face is the number of descriptors. Suppose I want to take into account not only the size of the captain's ship to predict his age, but also maybe the age of his daughter. Now, if I do this, I have two descriptors. So now I'm fitting a linear regression, but in 2D, so 2D plus 1, which is my output variable. Okay? So I'm fitting a plane. So that is a harder problem, especially since if I have very little data, then my problem becomes ill-posed or ill-conditioned, right? So what we see here is that the more descriptors I have, the more data I will need. And importantly, this tends to increase almost exponentially, unless you have specific assumptions. So in machine learning, this is known as the curse of dimensionality. Basically, more data may not be may not make the problem easier if there's more data means you're just describing the problem in a more complex way. It's what I call a needle in a haystack problem. So, this was an example about regression. Often the problems we're interested in are classification problems. So the idea being that you have a set of classes and you're trying to predict which class the object belongs to. So for instance, you might be trying to recognize handwritten digits. Here are a bunch of handwritten digits. So how many classes are you trying to predict to? How many classes are there here? Right, 10 classes, exactly. I haven't shown all of them, but they should be 10 classes. So then what you're going to do is that you're going to represent these objects. You're going to represent so what you're trying to predict from with some numerical descriptors. And so just to be able to visualize it here, I've taken 2 numerical descriptors, and then each one of these images becomes a data point in a 2D plane, right? That's because I've taken 2 numerical descriptors. If I took more, it would be a data point in an ND space. So then, trying to classify these things is trying to find separating boundaries between those data points, right? So that's a picture that you can have of a classification problem. We're trying to find separating lines or separating boundaries. One last thing. We're using some form of models to predict. They're models of the data, but they're not models of the data like in physics. They don't have to be mechanistically driven. And here is one example where we have a sine wave, and we're going to try to fit it, and we're going to use what looks like a staircase. We call them regression trees. So we're going to use a staircase of 10 constant value. So you can see there's a pretty bad job at approximating the sine wave, right? So then what we can do is that we fit a new staircase on top of this, you just trying to model the error. And we keep going, and each time, we're fitting the residual, and we keep going, keep going, keep going. And if we do this for 300 iterations, what we get is a pretty decent fit. Not perfect, but pretty decent. This is known as a boosted regression tree. The message I want to drive in here is that the reason we're using those trees, those quote-unquote staircases, is because of trade-offs. And one of them is a computational trade-off. Those things are very fast to run, so we can fit 300 ones of them very quickly. And the other one is a statistical trade-off. By controlling the amount of constant values we have on this, we're controlling the model complexity. So this is an idea of regularization, okay? One last thing about machine learning, sometimes we don't have labels. In which case we call this an unsupervised learning problem. And this is a example where I took fluctuations from stock market values. And then we learned to represent them in a 2D space. And we learned to cluster together different companies because these are companies co-fluctuating, and we learned the interaction between the companies. And that's kind of interesting because you can see here, for instance, all these are oil companies. Here you have some high-tech companies from Asia. So the Asian companies are co-fluctuating together. Somewhere in here, but we can't see it, it's on the side, they're the defense contractors. Okay, so this is a situation where we've captured some structure without any labels. Why is this interesting? Because labels are often expensive. Labels are often something where you need to have somebody labeling the data to bootstrap your problem. So unsupervised problem may be interesting when you don't have labels. Okay, just to wrap up about machine learning, so it's about, fitting predictive models, and there are several kinds of problems, regression, classification, or a large set of unsupervised problems. The important notions are that of overfit, so it's fitting the noise, of test error, that is not the same thing as strain error, of regularization, and of model complexity. That's a few key words on machine learning. Okay, So these days, machine learning is everywhere. It's used in image recognition. It's used in marketing, analyzing click-through rate. You can use it for movie or music recommendation. I use it for medical data. It's just used everywhere. So back when we started, why do yet another machine learning package? There were existing ones. So why reinvent the wheel? Chances are we're going to make it square. Well, why do it in Python? Real statisticians use R. That's what I was told. But I also have friends who are astronomers, and they use something that is called IRAF. I'm sure you don't know IRAF, but astronomers use IRAF. Economists, they use GOS. Maybe you don't know what GOS is, but that's what they use. Real coders, I'm told, use C, or maybe assembler. If you do experimental control, you're doing it in LabVIEW. If you're a Bayesian guy, maybe you're using bugs or stands. What I'm trying to tell you here is that there is a Babel tower of languages that are all, tailored for one problem. This doesn't scale, Even in statistics, we can't agree on which language to use. The Bayesians like Stan or bugs. Other people like R. So one thing that was important for me was to do machine learning in a language that was not specific to machine learning, because the real world is a complex thing, and I want to be able to plug things together. So that's why we chose Python. It's a general purpose language. It's an interactive language. You've got things like the IPython notebook, where you can type code and see it run, but you can also run it in a server in production. It's easy to read and to write. That was critical. Importantly, we're building upon a full stack that existed before data science was trendy, which is the scientific Python stack. It's been there for a long time. It's very mature. And the core object is the NumPy array. And Scikit-Learn really builds upon the NumPy array. It's a very poor data structure when you think of it. It's an abstraction over basically what in C would be a float star star. So it's just basically an abstraction of a pointer towards uniform data types. It has no annotation or structures, so that's a bad thing. But the good thing is it's completely universal across applications. You could be doing astronomy, you could be doing marketing, you could be doing medical data. Your data can be represented as a NumPy array, and that was one of our goals. So we have a lot of people who load data from CSVs and who come to us and tell us, why aren't your algorithms built with Panda data frames? Well, not everything has this structure. And Scikit-Learn is useful for other things. And something also that was extremely important for us is that NumPy arrays are easy to share with other languages. So you can pass a NumPy array to R without copying the data. And that was very important. You can read NumPy arrays from a disk or from database without copying the data. So for us, they're extremely useful because they allow us to connect to Scipy, which is a huge stack of numerical algorithms that can be applied basically to NumPy arrays or matrices. But we can also connect to something like Scikit-Image. So Scikit-Image is the same thing as Scikit-Learn, but for image processing. So we do machine learning, Scikit-Image does image processing. So if you want to solve problems like computer vision problems, then it may be useful to plug in Scikit-Learn on top of Scikit-Image, and then you can do image recognition. And yes, we can also plug in pandas, because if you have mixed type data, pandas is just fantastic. So I think the value of the scientific Python stack and the value of the Python stack in general is about these things that plug together. I would say the main value of Scikit-Learn is not Scikit-Learn. It's the fact that it sits in a bigger stack, and you can run a web server in the same language, in the same environment than your real-time analytics. And I think the R people are not doing this. So for us, what's really important is to have Pythonic code, and by Pythonic code, I mean code that looks like Python, and if you don't do Python, it's not obvious to you, but if you've been doing Python for a while, there is a certain feeling of something that looks like Python. And it's also about what I call being scipy-Pythonic, which is to be able to naturally plug in other things. that don't know about data processing or that don't know about machine learning, but they just know about the Scipy stack. So our vision is that it's about machine learning for all, which means that we're not targeting a specific application domain, and we're also trying to lower the requirements for machine learning. We want to be easy to use. We focus on this. We care about high quality, building a high quality library, which means that we also care a lot about the interfaces. We spend a lot of time thinking about interfaces. So APIs. And something that was very important for us from the start was about being community-driven development. It's about opening the development process to other people. And there were some decisions that were made from the start for this purpose. So I spent most of my time as a researcher, an academic researcher. So machine learning is a field of research that is moving on extremely fast. And when we started, colleagues who are researchers told us basically, you're just implementing old stuff. You're not implementing our new stuff that we've shown is better. And so there was a bit of a tension there. And when you're doing research, things like conceptual complexity are not an issue. And what I call conceptual complexity is that you may have an algorithm, a model, that is more powerful, but it may require you to understand it better and learn more. So this is never a problem. You can always come up with something that is more subtle, and it's seen as a good thing in research. Anything that is new and more bleeding edge is always better. And simple problems are seen as bad things. They're seen as soul things, they're seen as old science. Now, on the other hand, if you're in the field, if you're using machine learning, then actually, tried and tested stuff, which is often thought as boring, is good. You would like to require as little sophistication as possible from the user to solve the problem. And what we found is that API are more important than math. So we're sitting between, or at least I as a researcher, I'm sitting between those two worlds. And it's an interesting situation because you always have to do a judgment call between including something that is more recent and sexier in a sense, and wondering whether it's actually bringing value to the user. So one thing we try to do in Scikit-Learn is to be a bridge between this world of bleeding edge academia and actual useful stuff. And this is actually a hard problem, but this is one thing that we're investing a lot of time on. So what we've learned is that solving simple problems matters a lot. And if you solve them really well, then it matters hugely. So it's really, the first thing to do is really about solving the simple problems well. And then we're going to move on to solving the complex problems, maybe one day. Okay, so a few words about the tool itself, beyond philosophy. So it's a Python library. It is not a program. It does not come with a graphical user interface. This is a choice. The reason being that a library is more expressive and more flexible. It requires you to learn to code in Python, but it gives you more power. And because it's easier to include in an ecosystem. We want it to be as easy as pie, and that is an example of using Scikit-Learn. Basically, you're importing a model, and here it's a support vector machine. You're instancing it, so you're instantiating a support vector classifier. There you have your model, you can use it. So you can fit it, you can train it on trained data, or the X data is what you're going to try to predict from. So it might be images, for instance, in the digit recognition problem, and the Y are the labels that you're trying to predict. So it might be the age of the captain or which digit, okay? So you fit it, it runs, and then you have the classifier object, and then if new data comes in without labels, then you can just predict, calling the predict method, right? So this is almost the only thing you need to know. Now, of course, it can get a bit more subtle if you want things to work really well, But given data, if you're able to transform it in NumPy matrices, then you can apply this. So the model, the estimator, is our central concept. It is instantiated without data, and the reason being that we might want, to pipeline it or to dispatch it over a computing grid, but by specifying the various parameters. So for instance, if you think about nearest neighbors, you might want to take decisions by taking into account not only one nearest neighbor, but two nearest neighbors. So in this case, you're going to instantiate what we call the k-nearest neighbor algorithm, and you're going to tell it that you want to use two neighbors. And then you can fit and predict. So every estimator comes up with a bunch of parameters that are explained and that describe the different settings of the estimator. So when you call fit, you're putting two data structures in it. One is a NumPy array. X is a NumPy array, which might be sparse data, and it's a 2D data. It comes. The first direction is the number of samples, right? The number of observations you have, and the second direction is the number of features. Okay. So what you have to have in mind is that you're going to have to get your data in this structure: number of samples by number of features. It may require a bit of work, but that's how you can use Scikit-Learn. And the second, the Y array, is a 1D data structure, which comes with integers if you're trying to predict categories, or floats if you're trying to do a regression problem, okay? And more, we're supporting situations where it could be like a list of names if you want to work with names rather than numbers. Now, if you're trying to scale up, this might be suboptimal because strings take more memory than integers. All right? And then once you have the model, you can do several things with it. You can predict. Some models can predict, not all of them, but some models can predict. Some models know how to transform their data. So they might be data reduction. So I might have learned to go from a very big data set to a much smaller data set with less features that are useful. Or we might want to test how plausible our model is on new data. So it could be either only X data, if I've just learned a density model of the data, or X and Y, if I learned a link between X and Y. So not every data comes in as a 2D matrix, right? So going from data that is not in a vector form to data that is in a vector form and that we can put in a 2D matrix is what we call vectorizing. So this 2D matrix, we call it the sample matrix. And one example that is very common is that you have text data. You're trying, so you have a Twitter feed, so 140 characters, and you're trying to decide something about each tweet. So we need to convert this into something that's a numerical matrix, because this is how we work in Scikit-Learn. So the common way of doing this is simply to count word occurrences. So you're going to count how many times each word occurs, and you're going to do a matrix which has on each line a word in its occurrences, right? So it's kind of the word cloud representation. So your matrix is basically a word cloud. So the way you can do this in Scikit-Learn is you have a specific transformer, something that takes, data in and can transform data, that will be able to transform lists of strings into a sample matrix. Okay? So that's one specific example of how to go from unstructured data to the structured data that we need for prediction. One thing that I'd like to stress is that it is not hard to build a Scikit-Learn object. You can build one in your own code base. So you can completely build a Scikit-Learn transformer that will allow you to do vectorization that is specific to your application. And this is, if you have specific applications, this might be a good thing. Okay, so we have a very rich feature set, and I'm absolutely not going to cover it, but very quickly, in supervised learning, things that are often used are things like decision trees, especially random forests or boosted trees. We have a wide range of linear models and support vector machines and many, many other things. For supervised learning, we have many different problems going from clustering to dictionary learning or outlier detection. Something that's very important is that all these models, they often come with parameters that you need to set, like the number of neighbors. And so we have built-in cross-validation, which I believe Andy will talk about tomorrow, that can be used to set those parameters. So we have the whole framework. So this slide is a fairly old one, but the point of this slide is to say that we do worry about computational performance. And we do worry also about a trade-off. We're not trying to do everything we can to be as fast as we can, because this might incur a technical debt in our code base. It might force us to do things that are very complex or very ugly. But we try to do everything that we can and is not too hard, not too ugly. And it's an iterative process. We keep improving here. So compared to other packages, we tend to be reasonably fast. And what we found is that what we need to do is mainly worry about algorithmic optimization, and we worry a lot about minimizing data copy too. So this is, for instance, a comparison that was done a year and a half ago, comparing our random forest fit times to a bunch of other implementations. And what you find, so we can compare to, so it's Gilles who did this, and he can compare to every single implementation because not all of them are freely available. And because also it's a lot of work. But what you find here is that we're doing pretty good, at least for random forests. And I'm sure you can find random forests that are faster than we are, but we've put an effort here. So I'd just like to stress, well, I'll come back to this later, yeah. So what if the data does not fit in the memory? These days, it's cool to be working on big data that doesn't fit in memory and to be throwing at it things like Hadoop or Spark is even cooler. So these are the big buzzwords. But it's important to keep in mind that Hadoop and Spark are really made for very big data set, things that are petabytes of data that require distributed storage, a computing cluster. A lot of people, they have gigabytes of data. They want to do Python programming, nothing fancy like Hadoop. And often we find that they want to use off-the-shelf computers. They don't want to be running a cluster because a cluster requires buying the cluster and then paying the cluster administrator. And so I think these are the 99% use cases. So Scikit-Learn, if you know how to use it, can address them. We've been working in my lab on data sets that are absolutely huge, terabytes. And the core idea here is that we're going to be using online algorithms. So online algorithms are algorithms that can do partial fits. They can eat the data chunk by chunk, all right? So the idea is that chunk by chunk, you're loading data and feeding it to an algorithm that has a partial fit method, right? So iteratively, it's fitting. And so the kind of models that we have that can do this are linear models. If you use the SGD solver, so stochastic gradient descent. We also have clustering algorithms that can work online, and that can be good to see, like to have a reduced version of your data set that can fit in memory, that can be extremely useful. And recently, well, a year ago, we got a PCA that can work online. So that's a principal component analysis, and the idea being that if you have data with many features, like images, for instance. I work on images of the brain, and they have like 50,000 voxels. Maybe you can find a small number of modes of variation, like 1,000, that are really good to capture these images, the statistics of these images. So nowadays, you can run this on data that's absolutely huge, thanks to the incremental PCA. So the kind of patterns that we see to process very big data relies on things like on the fly data reduction. So suppose you have a huge amount of feature, then you can, if you have an estimator that can reduce the data, like a PCA or a randomized projection, then you can go from big data to a big X, not a big data, but a big X to a small x, okay? So in Scikit-Learn, you can do things like random projection. So that's finding a way of, if your features are redundant, it will summarize them fairly well. You can also cluster features together. And if you're working with observations with varying sizes, like words, the hashing vectorizer, which is a vectorizer that is stateless, can be run online using partial, well, it doesn't have a fit, it's stateless. So you can transform the data as it comes. Okay, so now I want to move on. So that was, I need to stress that this was a very short introduction to Scikit-Learn. Andy is really going to give a tutorial tomorrow that is actually with code and teaching you how to solve complex problems with the Scikit-Learn. I'd like to talk a bit about the project, about how it's run, because that's very important for us. First, you know, I think we worry quite a lot about having an impact. And having an impact is more like this than punching really hard. It's more about, you know, creating a chain reaction. So I think we've had an impact. And so because I'm an academic, I'm paid by the number of citations, which is a pity. It's useless. But anyhow, the good news is Scikit-Learn is cited a lot, so it's good for me. And the bad news is that not every contributor to Scikit-Learn is on the paper, and this is really bad, and we need to get another paper out to get more contributors on it. It's really hard to know how many users we have. It's like impossible. So the only numbers I can get is how many people are using us on Debian. So like one of the Linux installs. And we have approximately 1% of the Debian people, of the installs of Debian with Scikit-Learn. Another metric is that this morning I looked up and there were 1,200 job offers on Stack Overflow for Scikit-Learn. So I think we're getting a big user base. And what makes me really happy is that a lot of people are using us to solve real-world problems, so not academic problems. You know, there's these guys, for instance, Solido, they use Scikit-Learn to devise chips that are more energy efficient. I don't know how they do it. That's just what they told us. But I think it's a pretty cool application. Another really cool application is that OkCupid is using us to match people. So we're making people happy with Scikit-Learn. I'm very happy. So why is this happening? I think it's happening because we have a very big feature set. And the reason we have a very big feature set is because we have a very big team of people working on Scikit-Learn. And that's where the community-based development was crucial, and has been crucial, and it's still crucial. It's really hard for us to say how many contributors we have, because it's basically, you know, it's a 1/f distribution. We have many people who do very few things, but they're still very useful, and a few people who invest a huge amount of time. So what do you define as a contributor? But you know, if we want to include everybody, I think we would be around 400 people who have contributed something, and we have between 10 and 20 core contributors who are heavily invested in the project. Something that I think has been very important is that from the start, we've had one full-time programmer on the project. And it's very important because there's a lot of tedious work that needs to be done. And by now, I should correct this slide because now it's 2 full-time programmers. There's one at INRIA and one at New York Andy Miller sitting right here. So these people are crucial. I mean, they're just holding the project together. This number is a bit old, but the estimated cost of development is in millions, and this is all given for free to you. This works because basically there is a positive feedback loop on contribution, because I think people, when they're contributing, are getting back something. So one example of what this does to a code base is the random forests that I talked about earlier. So first of all, so my team was part of like the start of Scikit-Learn, and we don't do random forests. This is not something we do because it doesn't work on our data. For us, it's awesome to have people who came and contributed random forests, because then we can show it doesn't work on our data. But we would never had coded a random forest algorithm. And then second, so it was started as something, you know, somewhat slow. What's shown here is the runtime of different variants of random forest across the different releases of Scikit-Learn. And what has happened is that this runtime has gone, you know, smaller and smaller and smaller until the current situation where the random forests are really, really fast. This was not the work of one man. This was the work of many people working together, looking at each other's code, coming with different IDs. And so what we found is that many people working together makes better code and faster code. And the good news is they even tweet these kind of graphs, and then they do the slides for me. All right, how do you build a community-driven project? Well, that's my take on it. I think the first thing you need to do is you focus on quality. People will not join a crap code base. People will join a code base if they think it's a nice one, and they will want their code in it if they think it's going to make the code better, or they think it's going to make the code is going to join other good code. If you have bad code, you will not have contributors. I think it's extremely important to build great docs and example, because it's the same idea. The contributor is getting value from putting his code in your project because he's getting this good this good reputation and this good image. Then this is a point of view, but I think you should be using GitHub, and I think you should be using GitHub mostly because it's trendy, and it's been trendy for a while. So everybody's on GitHub, so be on GitHub. Now, point 4 is crucial and very subtle. I think it's extremely important to limit the technicality of your code base. So basically, if you want to do super fast random forest, you can use all kind of crazy tricks. I don't know, you know really good C++ compiler pragmas, for instance, that may allow you to say that your pointers will not be annihilized. And so that might make things faster. You can do all these things. And the more you do these things, the more you're raising the bar to contribution. At some point, you know, this is really a diminishing return problem. You know, at some point, there's going to be like a very small number of people who are going to be able to contribute in the project. And one thing we really fight for is to keeping this bar as low as possible. So of course, unfortunately, as the project becomes bigger, it becomes harder to contribute just because the project is big. But still, we're always on the trade-off of not becoming too complex, which means that if you try to be faster than us, chances are you can, but it's going to cost you something a cost that we're not willing to take. So another thing that is extremely important is that releasing and packaging. Release early, release often, package, get it everywhere. People would contribute to your code base if their code eventually reaches users. And finally, focus on your contributors. You know, don't forget the human factors. People are humans. If they work on the project, they need credit and they need decision power. And there was a great tweet by somebody, I don't remember who, a few months ago, who said, you know you're doing open source when something happens in your project that you have not predicted. I'd even say, you're doing open source when you as a historical project leader are contradicted by the contributors and they end up being right. And that's like the best thing ever. Because if they weren't there, you would have failed. So I hope this is happening in Scikit-Learn. Personally, I find it's a huge amount of fun to be working with the Scikit-Learn people. So quality matters. Quality matters extremely. So how do we keep control on quality? Something that's extremely important is code review, and we work a lot with pull requests. So pull requests, basically somebody modifies the Scikit-Learn code and then sends via the GitHub interface, sends a request to include this modification. And then starts a very lengthy and difficult process, which is that the different contributors look at the code and comment on it. So the first time this happens to you, this can be, I guess, painful. Because you get people arguing about your variable names, the length of your lines, and all these details. But this is very important for two reasons. One is it makes us all homogeneous. Because we all try to look at code, we all know the code base, and we all somewhat agree on the kind of decisions we need to make. And then the second thing is it actually empowers the contributor, the newcomer, because the newcomer is also learning how we do it. So even the newcomer wants to learn how we do it, and then at the end of the day, he or she has learned and is probably a better contributor, or he or she does not want to learn, but then means we have to do the job. So everything is discussed in a pull request. And the first thing that we tend to discuss is, should the algorithm go in or not? And that is actually a very, very difficult choice. It's maybe the hardest choice. And then we look at things like, are there good defaults? Defaults are very important because most people, they pick up the thing off the shelf and they just try to run it. So that's another difficult problem. Then we worry about namings. We worry about numerical stability. We worry about execution. Speed of execution, we worry about documentation, we worry just about everything. It's a lengthy process. It can be really lengthy, but usually what we find is that the quality of the code just increases, increases, and increases. And it's also, the reason it increases is because it's a collaborative process. Everybody comes in with, brings in different things to the table. Another thing that we found was absolutely critical was unit testing. So we're trying to test as much as possible. Our goal is to have everything tested. We found that, testing, so we're basically testing statistical code, which is a hard thing. But testing for convergence on all kind of platforms has basically made our code more numerically stable, more robust, because each time somebody comes in with a numerical instability, we try to transform this in a test and improve the code base. On top of this, we have a great bunch of what we call common tests, which are tests that we run on absolutely. I see Andy smiling because he was really part of this. He basically made the common test happen. And they're fantastic because, so these are tests that we run on every estimator. We just pick an estimator and we run the test. And this forces some uniformity in the code base. And I think that one thing people like in Scikit-Learn is this uniformity. So there's a saying in software development that is, if it ain't tested, it's broken. And across the years, I find this is true. If something is not tested, maybe it's not broken today, but it'll be broken tomorrow. Okay, so in software development, they often say, make it work. First you make it work. Second you make it right. And last you make it fast. Well, I like to say, first you make it work, then you make it right, and then you make it boring. So at PyData London last year, I was amazed to see that the talks were basically saying, the people were saying, we focus on feature engineering and on getting the data and on getting in. And once we get to the machine learning step, well, it's solved. We just use Scikit-Learn, the problem is solved. Which I don't think is true. There are problems that are not solved. But this is where we would like to go. Now, the bad news is once it's boring, it's boring. People don't want to worry about it. And so there's one thing that's called the tragedy of the common, is that there's a common resource, and because it's common, people are not investing in it. And I'm very afraid of it. So we need contributors, even to boring projects like Scikit-Learn. And even if you can't contribute, If you're in academia, we need citations. If you're in a company, we need testimonials. Basically, we need you to say that you're using us to be able to survive. Oops, I'm going to wrap up. So I talked about Scikit-Learn, about the vision, and the vision is really machine learning as a means to an end, finding the right level of abstraction, not domain specific, but general enough, and close to research, but not for research. We strive to have a simple API that's uniform across all learners, and we use NumPy matrices as data containers, so that is a pro or a con, depending on your point of view, but we think it's a pro. And we try to be reasonably fast for a certain definition of reasonably. And I think what makes the project great is that it's about many people working together and striving to have, as good quality as possible. So if you want to learn more, I'd really push you to go to Andy Miller's tutorial tomorrow. I think it's going to be much more in the nitty-gritty details. And I'd like to say that if you want to help with the project, you can also do this being paid. Both in France, in my team, and in New York, in Andy's team, we're trying to hire people who are going to be paid as programmers on the Scikit-Learn project. And maybe you can get a better salary going in the industry, but you can learn more by working with us, I think. Thank you.